All right, welcome to the second day. Today we have a few data focused topics. So the first lecture is going to be about Vlasiator data outputs, and then we'll have a bootcamp on this visit software that we use for monitoring runs and data exploration and analysis as well. And then we have the Analysator Python package bootcamp later today as the last session, and then we can have some free-form workshopping. So please, well, at least if we have the time for it, hopefully a bit more, but than yesterday. But feel free to suggest topics for afternoon, like if you have something that you would like to discuss in more detail. Please feel free to add those to the HackMD, and we can then pick up from those. And I would like to ask for you to during the first break, or if we have some interruptions in the program, please check out this visit software. You can install a local client of visit. So we'll start that the visit bootcamp with looking at that, and it would be faster if people already have it. We can have maybe a bit longer break to figure that out. But first, we'll have a bit of a recap of yesterday's topics and the benchmarking that we did. I have a full screen again. Thank you. So yesterday we learned that git clone recurse submodules, at least in theory, should give us a proper Vlasiator code base, but there appears to be some asterisks. So having the SSH keys indeed set up properly is something that should be done. We will probably try and change that so that you wouldn't need SSH keys to clone the repository with all the submodules. Then, well, we have the build libraries script that we will be updating shortly so that we can actually use that robustly. And also, just to note that we want to build our code to the HPC environment and profile its performance. And let's have a look at the scaling results, the benchmarking tests that we did, which are here. And there's some points to discuss. If there are other, where's my zoom? There. If there are still some missing entries, please fill them up. So let's see what we have here. This is way too fast. Scroll. So here I had a couple of my tests, the baseline tests for weak scaling, and those are about 900 seconds. And these weak scaling tests are such that we keep the workload per processor should be constant. So if we get some bad scaling here, so that we increase the node count and the domain size, then we can see that there's something to be improved in the communication. So we see that there's been a bit of an increase in the runtime, so that's not quite ideal. Quite ideal here. I was kind of hoping that this would have been a bit faster, but this guy here is actually having pretty similar results as this one. Well, it's the same configuration, so that's not interesting. This would have been interesting to see as well, because there's the having this box in like a evenly sized, that I think that should have been a bit of a helper there. But once we go to the thread and task balance, there we can see actually a huge difference here. So going to having very many tasks per node, so that there's practically no threading here, made the run about 30% faster from the baseline. So this is pretty fast, and of course this is good. But once you go to much larger runs, then you might run into issues with the memory footprints, because these are now very small domains that are doing the computation and then trying to communicate with all their neighbors. So 64 tasks and instead of 16 tasks. So that increases the communication by quite a bit, and the buffers relate to that. So this is good for this particular case, but once you start using larger runs, then that's going to be a bit of a potential issue. Then you might want to actually increase the thread count. Jan has been pretty busy with doing some extra tests. He has been done hyper-threading tests, so having this 2 logical threads per core, that's this one extra flag, and increasing the number of cores that are being set in the SPatch, the slurm file, so that there's like a double amount of cores being allocated there. So that gives us just like 20 seconds over the baseline. So there's a bit of an improvement there, but the results may indeed vary a bit. I see that there's been some tests with lower core counts with hyperthreading on and the same task counts. So these would not be using all the cores possible, which well then results in larger runtimes. So this is underutilizing the equipment that we have. There is one test with this looks to be similar to this guy, which has a different load balancing algorithm. And this RIB is the one that had this funky Picasso-like pattern. For this case, this actually is a bit slower than the baseline case here. And then Jan has also done doubling of the velocity space resolution tests here. So this is probably much more realistic in terms of the velocity space extent, and the runtimes correspondingly go up quite a bit. So we have 8 times more velocity space cells there to propagate.
So let me comment from the offside. Hello, if you hear me. The 32 task case actually went over 200 gigabytes memory on one node, so it was reaching the limits of what we can do.
Yes.
But as we see numerically, you'd have thought that it's 8 times heavier because we double resolution in velocity space, but it's actually only 2.5 times slower. So there is more efficiency, and it's not a straight factor of 8 because we are still a rather coarse resolution in velocity space. So we are cutting the exponentials a bit differently than just a factor 8 here. If you resolve better, you'll see more of an 8-fold scaling in this kind of test.
Yep. It's the rough scaling of that, yeah. I think we can then go forward. Do you have any questions about this very thick spreadsheet probably, but do you want to ask them? I guess not.
Well, how did it go for the people who reported numbers? Did you see anything surprising, or do you have any questions on the setup, or?
Was that for audience?
Well, for all the people who put their initials and put some numbers here, I see that it wasn't only me and you. So how did it go? Did they have anything surprising or any comments on that they'd like to?
Was it easy to run those once we got the binaries? No one in chat. No comments. No morning coffee yet.
It's the 9 a.m. effect, yeah.
Yeah. Yeah. Well, this is the thing that I commented on this fast configuration with some caveats on the memory footprints. Yeah, sure.
Well, if you run a larger team, you think that, oh, that's faster here.
I'm not quite sure what you are asking. So
You're saying that, like, the one time that was
yes.
you think that this could be within?
We probably would get the same effect for the performance, but the thing is that then there's going to be extra memory overhead, so you might not be able to run the simulation anymore if it's large enough. You won't be able to fit it in the memory. All right. Maybe then let's go forward if there's no other questions on this topic. But a few words about actually about running these runs, about babysitting the runs. Now that we got into the had some taste of running these simulations, and these are pretty fast ones. But then once we have the long simulations, we really do want to keep an eye on the progress of and the cost of the simulations. And it's pretty important that you can save your progress in the simulation. So that's why we have these checkpointing files or the restart files. And we'll have a look at the restart files a bit later, or talk about them a bit. But just to show how we do this in the config files, we define a wall time interval, so in seconds. So in seconds, the interval at which we print out this sort of a restart file that stores the simulation state from which we can pick up the simulation afterwards. So this one is now a bit less than 8 hours. So that after 6 restarts, we will stop the run. This also will tell the simulation to print out 6 restarts worth of data, and then it will just quietly close itself. And this has been measured so that when we have 48-hour slots, or however much this actually is, but yep, that's fits. So that the last restart is going to be written a bit before the actual computation time expires. Because if the computation time expires, then we might get kicked out of the server and lose all the data if we haven't saved it recently. So we have a bit of a safety margin here in case there is some hiccup in the file system, like if the write takes couple of 20 minutes or something instead of the 90 seconds, I guess, was at this point was in the production that we were writing the restart file. But it may happen that there are some hiccups in the file system or the network on the computer, so we want to have a bit of a margin for error there. And once you have these restart files, it's quite simple to pick up from a restart file. So you just have this --restart.filename parameter, and then here goes the file name. And we have this sort of a handy snippet here, so that this will find the last written restart file, and it will just use that. So this command will check the restart files, and they will be sorted by the timestamp that we write into the file name of the restart file. And takes the last one and then feeds it into the run command. And we can also force writing a restart file if we see that there might be something going wrong, or here that there's going to be some maintenance break, like unannounced or something, some problem somewhere. So we might actually want to manually tell the code to save the state. Then we can just create a file in the run directory, say this sort of a stop file, and the file name will tell the command that the Vlasiator is looking for. So if you do this touch command, which creates the file with the file name stop, then this will tell the run to stop with saving a restart file and then gracefully exiting. And once when you give these commands, these files will be renamed with a timestamp, so you'll get an accounting on what you have been doing with the run. So you don't have to then think about what has been going on. There are other options. So just save, restart, and keep running, and then the kill command that is just like stop running right now. Don't save anything. And then there's these two dolp and domr commands that are do. That should be a bravo, not a hard P. Do load balance and do mesh refinement. So you can force, for example, a load balance. If you see that the runtime has spiked for whatever reason, you can try and rebalance the load if it would help with the performance. Same with do mesh refinement. So if you suspect that there's something going on with the mesh refinement, that there's some region that hasn't been refined lately and should be refined, then if it's just waiting for a mesh refinement cycle to kick in, then you can also manually launch that one. Questions on this portion at this point, and then we'll go to Vlasiator outputs. So transitioning into the proper topic of this lecture. And we have three main kinds of data. The log file, which just lists what is going on with the simulation and prints out timestamps and how long it has been running. And this was indeed what we were looking at yesterday with the runtimes. And then we have a diagnostic file that you can configure with the config file. So you can get statistics of how many velocity space blocks you have, mean, max, average. Well, mean and average. Yeah, pick your favorite word on that. Min, max, and average maybe. Timestep limits. You can indeed select what you want there. But this is nice for tracking the development of populations and how much of memory those populations are taking. And the actual data, the actual results are stored in these VLSV files, and we'll dig into these a bit more. But I could actually quickly show you some of these log files, what they look like in a bit more detail. So let's go to the example runs and go to the scaling and baseline. Yes, now we also have this visible, this bottom row. That is great. So here's the log file for the scaling test that the baseline that I made. So it writes here out like what are my parameters, what are how many tasks, MPI tasks, and how many threads I have. Then it starts to log that. Okay, we have the Sultan initialized. Load balance has been done. We managed to set the initial state of the simulation. Great. Then computing the dynamic time step. So here we see that okay, now this 2-second time step seems to be good for this. And this accounts for the spatial translation of the velocity distribution functions, the velocity space transformation, so acceleration step, and the field solver time step. So here, even in this guy, the acceleration step seems to be the case. And that's the initialization, and then we get into the main simulation loop. Here we do the filtering of the movements from the spatial grid to the field solver grid. So that's marked there, and then it just starts to tell that okay, here's the time step. We have that many. This actually might change that this sales output goes to diagnostics output also. And that's a new development, and we are not quite sure where we want it. But then it looks also like, okay, now we wrote out the system data, and it logs how long did it take for us to write it and how much did we write. Gives you data rate, and this is something to keep an eye out for, especially for restarts that we want to be able to write quite a lot. So in the production run, if we write this 5 terabyte restart file in 90 seconds, that data rate is pretty substantial, and we do want it to be that way. And this can be optimized with these loose striping parameters that are introduced in the materials. And then we see that it's just rolling forwards, writing some files and doing some load balancing. And there should be also a mesh refinement somewhere. Where is that? But yeah, these are going to be a bit longer. Let's see, refine. There, adapting refinement. So there you can see that we refined some 500 cells and didn't coarse any cells at this point. That will change a bit as the simulation progresses. But that's the gist of it. And if you want to automate this a bit or make it easier for yourself, you can do some grepping on the T-step. So let's say grep T-step and log file, and then you can get a bit more condensed output, and then choosing these keywords nicely and using some bash magic like set or org, you can extract these, and then you can start plotting time over a number of time steps, so you can get a graph of the performance and so on. So that is left as an exercise on how to do that if you wish. The other one is the diagnostics diagnostic.txt, and here we have been just storing the velocity space blocks of the proton population. So we have min, max, sum, and average over the spatial cells, and we can see how it develops over time. And we should see some evolution here in the sum and maximum value as we push in the plasma, and it starts to interact a bit with the existing plasma, which we do. So the block counts have increased here, and I guess they should also stabilize here. Yes, pretty much. That's probably most of these changes coming from grid refinement at this point. So we increase the number of cells that have these velocity distribution functions. So then we also increase the total amount of velocity space cells there. Okay. Then to the actual data, and so already 30 minutes, trying to keep track of the time. But yeah, the VLSP files, and this file format is a homegrown file format, and it is definitely optimized for this parallel input and output. So it's easy and fast to write from a large collection of MPI tasks. And the first type of VLSP files, we have a few types. So the usual types of VLSP files are first here. So the restart files, these store only the primary quantities that are required for the restart process. And these variables are a bit different from the ones that we will be looking at. But you can still access them and plot them. It will just look a bit different. But this is so that we don't introduce extra weight into these large files, because these include the primary data, so the velocity distribution functions everywhere, and then the field solver grid primary values that are the phase averaged magnetic field values and the edge averages of well, does it need the E? I think it does. Does need to store that as well. But then we save these in this format, so restart dot something. This is going to be the time in seconds and of the simulation time, and then a timestamp with down to second precision. And yeah, these are big files. So the 5 terabytes is pretty large, and it had been still growing. Now the plan is to cut down a bit on that by coarsening some portions of the simulation, but we'll see how that goes. Then we have the bulk files. That's just our naming convention. So these are configurable outputs. There's a listing on at least some of the variables that you can list in your config files to select what kinds of outputs do you wish to have. But this includes indeed the plasma bulk quantities like the velocity space moments. So density, velocity, pressure tensor, and the pressure tensor is the full tensor, because we can calculate that directly from the distribution function, and then we can have all the terms like the electric field from like the total electric field, volumetric average, and the terms that go into it, like the Hall term and the electron pressure gradient term and whatever you wish. There are some included data reducer operations, so that you can derive some quantities to be saved during runtime into these files as well. And you can save VDFs into these files as well. It's good to only save them at some points, because that will be prohibitively expensive if you want to save them everywhere, but you can configure them with some strides, so you can get like a sparse grid, like, okay, we have in this cell, and then let's go a couple of Earth radii that way, and then have another spot there where we are storing the velocity distribution every output interval. And we use something like a naming scheme that looks something like this. So kind of the cadence in seconds, and then the index of this bulk file. And you can configure several bulk output writers with different names. And so you can, for example, save the field solver variables at the lower cadence. Since when we have the spatial AMR on the Vlasov grid, the Vlasov grid is actually pretty cheap to store, like in some few millions of cells. So that's pretty cheap. But then at the highest resolution, the field solver is going to be pretty expensive to store at just like gigabytes per component or so. But yeah, the solution is to write these FSGrid variables at the lower cadence if you want to have these high resolution original field solver quantities at your disposal, at least as a check on the progress of the simulation. Yeah, these are the special cases. One extra special case is storing the magnetic field Jacobian for the initial condition, or rather the background magnetic field. And I don't think we have actually mentioned this before, but in the solver we use two different magnetic fields. So one is the background magnetic field, a current-free magnetic field, so that we can put the terrestrial dipole there, because the values of this dipole field can be quite large compared to the perturbation of this field. So the actual magnetic field that we propagate, so we can separate the propagated field from the constant field. And this is numerically a bit more precise, so we don't get any rounding errors with floating points there. Well, some, but not as bad ones. But it happens so that Vlasiator itself is kind of the handiest tool that we have for computing the Jacobian of the magnetic field, both for the background and the perturbed magnetic field. So we can actually configure it so that we save the background field Jacobians at initialization or afterwards by running the Vlasiator code with a special flag. And then we can combine these background field Jacobians with runtime Jacobians of this perturbed magnetic field. So we can then do all sorts of nice analysis with very accurate Jacobians. So like calculating the curvature of the magnetic field, for example, from the exact values that we can get from the solver, instead of using some volumetric average on the spatial grid that might have been or has been downsampled from the field solver grid. Like post-processing that can be a bit inaccurate. And then we can also save the initial state of the grid with lots of BDFs and bulk file like variables if you want to be sure that the initialization is correct. So that's pretty much about the VLSP file types that we output. And then maybe more interestingly, well, a pin on that, not quite yet at the data, but let's look at the file format first. So we have our own library for handling this file format. This is the VLSP library. And yeah, this is optimized for the runtime performance. direct parallel I/O writes, but this has some implications on how the data is laid out in the files. And the Analysator Python tool is built to read and analyze these files, and Markus will be telling you about this later and with some exercises. I see there's a chat message. So there's a question about velocity distribution functions being huge. Yes, they are. And yeah, that's the reason why we have the spatial grid mesh refinements. So we don't need to have quite as many points in physical space. And the production runs also are running on single precision, so that takes a bit. We can run that on double precision, of course, to check that we are doing good physics, but that is not strictly necessary. And we have some projects ongoing to store compressed versions of velocity distribution functions. So then we could maybe have even high cadence approximate velocity distribution functions in the bulk files. So we are looking into this, because indeed we can run out of quota on our runs with the restarts racking up quite fast. So that has actually been a bit of a bottleneck at some points, that we were almost more limited by the bandwidth of removing files from a supercomputer than generating or than running the simulations. But yes, we do have some strategies for this. For the restart files, we really shouldn't do this, like compression, or there we need to store everything, of course. But for the bulk files, those we just have very sparse outputs of PDFs, if at all, and that is configurable. I hope that yes, thank you. So let's see a bit about the actual file format. So these are all also gone through in the material. So the format is such that we first have a block of binary data that has been stored directly from the MPI tasks. They can figure out where to write them in the files, and then after the write, we will add a footer at the end of the file, and that will then contain the metadata required to reconstruct the data. It describes the meshes here, and then these XML tags and the attributes here describe some of it, and then there is a pointer to the file. Like at this byte offset, we have the data that has been described by this XML tag. So these are giving the specifications for the spatial grid and the field solver grid, and the associated data is stored at these locations. And then we have some parameters, so just single numbers or arrays that are not tied to the meshes. And then we have the actual variables that have been stored with some size and data type, and the specification of which mesh this is associated with. And for example, this is the cell ID, which we will get back to a bit, and you will hear quite a bit more about those later today. And here's another one. So this is now the field solver magnetic field variable stored on the field solver grid. And usually the variable naming is such that we have the FG for field solver FS grid and VG underscore for the spatial grid or the loss of grid. And a note about this guy, well, it's a magnetic field vector, and this is the primary quantity. This is the phase averaged magnetic field. And even though if this is associated with the field solver grid cells, and then the actual data values are still the phase averages of the normals to the phases at the lower end of this cell. So if you plot this as let's say pseudocolor plot as cells, then you actually are plotting over the whole cell the vector component that is associated with the phases of that cell on one side. So you have this sort of a centering issue there. So that's why we usually use volumetric values, volumetric averages when we then analyze these. They are a bit easier to approach. And I guess there's a note in the chat. And,
yeah, there was a very smart question about how do we manage to not have enormously huge velocity distribution functions, which is of course a correct question. If you do a Vlasov simulation without putting any thought to that, you'll quickly run out of memory. And the question was, how do we manage to make them not use hundreds of terabytes or exabytes of RAM? And the secret sauce of Vlasiator is, of course, the sparse velocity distribution function. I'm not sure if we should go into detail about this now. Jan already linked the reference about that.
Yeah, Marco had answered it also already. So I think now Dimitri has. We have Dimitri covered there.
Yeah, no, I actually just was thinking about just writing how to write things in the file. So yeah, but yeah, indeed, the sparse velocity space was also in yesterday's slides, but that also is a very large contributor to this pruning down of these distributions.
Yeah. And primarily the sparse velocity space is the reason why we don't use any pre-existing data formats like HDF5, because they don't really deal well with sparse grids at high dimensions. That's why we defined our own VLSV output format.
Indeed. So because of these decisions, you can now get to enjoy the VLSV data format as well. Yes, then we get to the kind of the meat, so the variables, or at least the variable types. So I kind of already mentioned that we have the field solver variables with the FG prefix, at least usually, and then the spatial grid variables with this Vlasov grid initials here. And these are stored from the AMR grid that has this funky load balance, and the ordering of these variables as they are stored is kind of special. You cannot really assume that there is any ordering for these values, and that's where the cell IDs will come into play. Then the FS grid variables are laid out quite simply, so you have a blocks of these ranks, and then you just dump those in order, and then you can reshape those and place them into this uniform array back quite easily. Then we have also the ionospheric grid, and these are prefixed usually by IG. And this is a triangle mesh covering the ionosphere with the data both on the triangle faces and the vertices of the triangles that can vary a bit. And then we have the velocity space variables, so the phase space density that can be stored at some points, and yes, it is stored as the sparse velocity grid. Let's see what's in the chat. Yeah, there's the HDF5 also, yeah, got mentioned. Good. Now there's that thing I have here, quite annoying. Can I move this thing? Oh no, it's a Mac. I don't know Macs. Yes, yeah, as I was mentioning, the ordering of this data, if you start to go in some X, Y, Z ordering here, then the rank from which you are writing that might change abruptly and pretty weirdly even. So this interesting load balance indeed requires that we have some way of tracking that, okay, this block of data in the file is related to this particular cell on this three-dimensional mesh that may or may not be refined. Usually it is refined. So we have this cell ID tag, which is just an integer number, which can be calculated so that it is unique for each cell despite the refinement level. So one number will specify exactly where we are in this grid and at which refinement level. Or well, with some metadata, so that you need to know the size of the base grid, so the lowest resolution grid. So if you have how many cells in this direction, and then you calculate an ordering based on that at one refinement level. And then if you want to have describe a cell that is at a higher refinement level, then you just add on top of this number with the corresponding size of this refined grid if it were on the whole domain. So those indices will just get larger, and the cell ID as well. And this is quite a clever way of going about this, and it gives this kind of an octree like indexing. So there's some useful idioms here. So sorting by cell ID, at least in unrefined meshes. So then you can get a regular array out of the data if you read the variable cell ID, and then use that to sort another variable that has been read in some order, because the cell IDs will then give you the ordering based on this one. So that maps it to a regular grid. And Markus will be giving you some examples on this. But yeah, this assumes there's no mesh refinements, and these mesh refinement tools we have been slowly adding into Analysator as well. So it's starting to be a bit more complete now in that respect as well. And the FS grid data layout is a bit easier to handle because the FS grid ranks look like this. So you take the data that is on this process in this cube, write it to the file, and then you take the next process and write it after the other. And so end to end, you write all these blocks, and then you can, as long as you know how many blocks there are and what are the corners of these cubes, then you can place and reshape the data into this into a regular 3D array that might indeed be pretty large array. And that actually concludes the slides I had here. It would look like, yes. And that is 9:53. We can have a quick look at the at the listing of the variables that we have in the materials here. And these are the ones that you can use in the config files to write different sorts of reduced variables or just variables. So for each population, you can get populations and then velocity. Then you will get the velocity for each population sorted by population. And for example, there is a option to get the non-thermal part. So this assumes how was it now? That all portions of the velocity distribution function that are faster than from the mean velocity by some or distance from mean velocity is larger than some threshold of, I don't know, few thermal velocities, that these are then the non-thermal part of the population. And then you can save the density and velocity, bulk velocity of the non-thermal portion. So if you have some force shock beaming, then you can kind of separate this already during the runtime and obtain some statistics over the whole run on that. You can monitor the loss from the sparsity of the velocity space, load balancing weights, time step limits caused by the environment. This is not quite a complete list either. Especially missing is ionospheric variables and some derived values that we get from doing the ionosphere, since doing the ionosphere requires doing the mapping between the ionospheric grid and the simulation domain in the magnetosphere. So you need to trace field lines. So why not trace the field lines everywhere and see, for example, if these which of these simulation domain cells are actually connected to the ionosphere. So we can get open-closed boundaries or flags for each cell in the whole simulation. So we can get, okay, these cells are connected along backwards and forwards along the magnetic field to the ionosphere. So these are really closed magnetic field lines, and then we can check that if we have field lines that are cells that are connected through a field line to the north or south pole and then being open in the solar wind. So we can partition our simulation domains like this nowadays. And yeah. Any questions then on this topic? Seems very quiet. And I see that there is also coffee there, so we can fetch coffee and then. Yes, sure.
So I was reading through the tools there for VLSV extract.
Yes.
Do I understand that correctly, that you can use the extract tool to extract data from just certain point in the entire
Yes.
data?
That extracts the velocity distribution function from that particular cell.
Yeah.
As long as there is velocity distribution stored at that cell. So for restart files for each cell and for the bulk files at some cells, if we have bothered to save them.
Yeah.
So yeah.
So you do only the velocity distribution function?
With this tool, yeah.
Okay. So not the density.
Yeah, I mean, you can use the Python analyzer package to to fetch those and interpolate on the grids, and I think we also have one tool to do that from the command line as well, somewhere laying about.
The primary reason why we have VLXV extract is actually when we are developing Vlasiator and testing, we take output from an old version, output from a new version, extract a certain VF, and then compare the two files from the old and the new version. That's mostly actually what we use it for. For most of the actual scientific analysis, we just run the Python tools and run whatever analysis we want using them.
So, and VLSV extract is writing a VLSV file, as it says on the screen of Marco here as well. So that can be then opened in Visit.
Yeah.
So in historical order, we wrote VLSV extract very early to see what we had in the simulation, but the analysator Python tools came a few years later. So.
And the other tool there is the VLSV diff that can be used to do differences between different VLSV files, as the name would suggest, and yeah, that could be then used to do the diffs.
But similarly, this is mostly used for technical development work, checking versions. It's not really used for scientific analysis.
Yeah, I mean, time differences could be done and written out into another VLSV file. That's possible.
Yeah, there is uses, but generally speaking, I don't think it's.
Yeah.
I'd recommend to get it working in Python rather than trying to use this tool. But yeah.
Yeah, how does it handle mesh refinement, by the way?
It doesn't. It assumes that the meshes are identical.
Yes. All right.
Oh, yeah, yes. So maybe you already said it, but I missed it, or we will come to it later. But is it possible to get like data for like a virtual spacecraft? So like the data for just one point?
Yes. Yes, it is. I believe Markus will have examples.
Okay. Then.
Right. Is it coffee time? More questions? We can have questions over coffee as well. A note, though, the next session will be about Visit and how to use that one. So for that one, we would like to have everyone to install the Visit software on their local machines. Hopefully that is possible, and hopefully you have been looking at how to do that. So you can get it. There's a link in the material to the Visit website. So please get this one and the 3.3 specifically. It should be pretty straightforward to install it on your local machine, and then we can configure the client server then at the start of the next session. So let's have a bit of a break and get ready for this one. All right. Is my mic on? I guess it is. Cool. So, hello?
Yeah, mic is on. We can hear.
Great. So, the topic of this lecture then is the Visit software and how to use it. This is going to be a very hands-on lecture. So, if you have not yet installed the Visit software, please do it now. Is there people who have it, don't have it? Have you installed Visit? Anyone? Yes, at least someone. Great. So then, to make this a bit faster, I have prepared this host XML file that is on the materials website. So please download it, and this time I checked that this really works also online, not just on my own branch. So you should be able to download that and place it into this sort of a folder. This might actually be a bit different on Windows, and on Mac I think we'll use this one. But I can also show if you'd can't find where to place this. On visit, on Windows, I think that should be under Documents. Documents with Documents and Visit folder. But the gist of this lecture is to follow along plotting on this lecture. So we can start by launching the visit screen, and yeah, the visit software is pretty notorious for having lots of windows open at you, especially after you have been using it for a while and saving some settings. Then it will also save windows that you have open. But there are kind of two main windows. This sort of a, well, this is the main user interface window that you can control to open files and set up plots and so on. Plots will come into this window here, or rather the pipelines used to build the plots, and the plots will be shown in this sort of a viewer window. Now, are people comfortable with the host file? Do you think you have that in place? Yes. If that is in place, you should be able to click just on the Open button here and change the host from this drop-down to LUMI-PEPSC. So Open and host and LUMI-PEPSC. It will take some time loading modules on LUMI to launch
cool.
the metadata server. Yes.
If you send them all to the debug partition, it's going to be clogged.
Yeah, let's not do that. There's also the small partition there, and let's indeed use the small one. And while we wait for this, I can also note that you can go to here in the main window to Options and Host Profiles. There you can inspect the settings for the host that include the address of the server and setting SSH and usernames. And yes, please do notice that I forgot to mention, go to the host profiles window and change the username to match your LUMI username. It will not work if you try to access it with my my username.
Who knows? But it shouldn't work.
Yeah, at least it shouldn't. Do we have any success on this front? Squinting. Are you in? Great. How about others? Confusion, questions? Okay. Well, let's wait for a bit, and I can yammer on a bit. So the viewer window I just mentioned, then file open, yeah, there's the host and then host selection, and then you can navigate with the path here, so you can start also to go towards our Scratch files and so on. But kind of a thing about the visit plotting pipeline is that once you start to add plots into this pipeline, the way visit handles this is by looking at the mesh. So the geometry, so where the data points are and how they are connected to each other. So the topology of this data, and then when you know the topology and the geometry, you can start to do some geometric operations and modifying this mesh. So for example, taking slices through this mesh, which then generates another mesh with points on this slice plane and then their connectivity. So you get the faces on this slice, and then Visit can sample the data onto this slice and plot it. And you can chain these operations. So you can slice a cube with a plane, and if you take another plane and slice it again, then you will have a line topology afterwards, and so on. And we'll see some examples of these operators during this hour.
I'm sorry to interrupt, but can you just move the file open window just so we can see what the modifications you did for host profiles?
Host profile, just you change your username. And then click apply. One of the most common head scratchers with Visit is forgetting to press apply and then wondering that why anything hasn't happened. In the launch profiles, we have here two options, debug partition and the small partition. Let's use the small partition then when we get the chance to select that. I'll show you that soon. Otherwise, the debug partition will indeed be clogged full of our runs, and then no one will get anywhere. But let's have a look at our sample run Mercury 5D. So you can find that here in the launching to client server, the path to that one. But if you are catching up, and you can navigate here to the bulk folder and open this as a database with file grouping set on. Yes, question? Let me get there and let's have a look. Let's have a look. I have used it on Windows some time ago on my own PC, but yes. So you have it here. Right, that's just start menu. I think it goes into your user folder or your documents folder.
Yeah. So,
Visit, there it is.
wait, where was this? Okay,
Documents
for me,
and visit.
but I was, but it's the one that to me, it's the one that is connected to my phone.
That shouldn't matter.
No, it doesn't matter.
Yeah.
I have two. One in my own drive, one.
Yeah. The one that Visit defaults to, Windows defaults to. That's the one. Yeah. That's definitely a note for us to add that into the slides or the material. Right. So I'll go ahead and open my, or at least get the host options. When you first open try to open a file, it will then prompt you on launching a compute engine. And here, please do select the small partition. And here you can set some settings, like time limit on your run. Let's do maybe 1 hour now. 1 hour slot. Project bank account that has been preset already also. And number of processors to use. I will recommend having at least 16. I think I will have 32, make it a bit faster. The Mercury plotting was surprisingly slow when I was now trying it. But yeah, use the small partition indeed. How's it going on the Windows side? Okay. Let's have a look again.
So try just like open this, and then I try to change now to LUMI. Then
Yes, you need to change the username. I think
so then
you should be able to do it from there. I don't know if it will then, will it then get the SSH key? I think it should.
okay, so
Maybe. Let's try. Let's try. Let's be wild. Okay, it wants password, but yeah. Then that's also fine. Yeah, you can log in with password as well. Uh-huh.
okay.
No.
You didn't get this. Wait, no, but I think I tried to do something.
So what does it look like there?
Is it files or options?
Options, host profiles. There you can, those are other host profiles. You don't seem to have the LUMI profile there.
Exactly, that's fine, that's fine.
But it found it for you.
When I go to open file.
Yeah, it is there. So I'm guessing that you put it to the wrong documents folder after all. No, but the visit is there, so that's very strange.
Supposed to be in host? It's supposed to be in host.
Hosts, yes.
Maybe this.
Oh yeah, reload might indeed do the trick. Yes, great.
Wait, should I be going to? I changed.
Yeah, you can options and host profiles, yes, and there you can change the username, and these are now the other profiles. Let's go to LUMI-PEPSC, and there you can change that. Oh yeah.
Okay, so I just post this.
Say apply, and then you can close that window. And after these edits, you might want to actually say options and save settings as well. Then it remembers your username.
Then I could potentially open.
Yes. Still wants your password. There, no, that's fine. Just the username, and then press apply.
But
Why is it not accessing now? That is interesting. So we have people who have gotten into LUMI, right? Great. Have you been plotting already? Yeah. Well, you can go forward there as well. Yeah, just use the small partition. And your username and password are you typed correctly. And is it now? There shouldn't be any access restrictions from like networks. Different problem. So do you have the same issue there? Host key is not cached for this server. Okay, so that's oh god. UTSSH yeah, cache. Can you enter commands into that window? You say yes there.
Yeah, I just like it. I'm not sure.
It might not actually. Yes, there's a thing with Windows that there was some update on the OpenSSH things. Oh crap! This is going to be a bit of a troubleshooting thing. How do we do this? So you all three have Windows laptops. Well, that should be fine. This and it says access denied. It's not some other error, and it's yeah, should work. Do we have any specialists on Windows SSH things here? No. There's a problem that we cannot get the SSH that is contained with Windows now to work with the visit that on Windows. I guess that's some older version that they actually use there, and that now seems to be not working. There is something in the chat. Is there any help there? I did do this at.
I can handle the chat.
Okay. It doesn't even allow with password, so that's annoying. I think there could be. I have some old notes on this somewhere, but then I don't remember where. Not even sure if this is now the. I hope I have documented this somewhere. is the I wonder if this is now something that we could use here. So I encountered something back in the day with Windows, so that I had to specify this SSH commands separately, and that is actually, I think that was for Linux. Still, there should be an OpenSSH implementation with Windows nowadays in use. So where it would be. Let's see, Windows OpenSSH. Then. So do you have an SSH client on your Windows machine? Like, do you know the path to that? Yes. I mean the actual SSH client software that you call from the command line. Okay. Yeah, if you can find that.
Okay, sorry.
Yeah.
I'm answering to Louis here. This is pointing to a script which is in a different project, and that's why you get permission denied. So Marco, the module.sh it's requesting is project 287. In the chat, there is a message from Louis. So he got the engine to start, but it failed on that. So there is a. So I'm not sure where that is. Is it in the install? So can I go and hack in the install, or is that in the host profile?
No, it's the module sh. That should be that should be in the folder there. But let's.
No, it's in the host profile. I see there is a source in the host profiles, which is still pointing to the old name.
Yeah. Okay, that's my bad. That's my bad.
Okay, but I can continue from there.
Yeah.
Have you copied the script in the? Well, okay, I'll proceed. Louis,
Yeah.
I'm still looking at your issue, and I will stop talking here.
Okay. Yeah, but can you modify the path there then?
So I can post a pull request in a few minutes. I'll post the path to put in the host profile in the chat in a few seconds.
Let's see. Oh, right. Yeah, that should be modified. True. Sorry about that. But the Windows SSH, I mean, there's the option in the host settings that you can specify the SSH command to use this on this line. So it could work if you can find the SSH command that you use to launch SSH on Windows. You could also just try to click this, if this is indeed in an alias for the Windows SSH client. It needs an regular open SSH implementation. I couldn't use it with putty some time ago, but the Windows's own implementation actually worked. I'm not sure if that's something that you need to reinstall separately. Let's have a look at the Windows again. How is it? Okay. Copy the path to that file, and let's place that into the host config. You probably need to kill the visit session there. Can hang up when you are. It could be just as simple as just tapping the use SSH command line there in the visit host profile setting. Yeah, I'm not sure if you need to specify the port. No, that looks the same. If you go to your Windows command line and say just what is the command you say there for SSH, just SSH. Okay, well, I mean, that should then also work there. Did you try just having the SSH tag there in the host profile? I mean, like so. Let's try with that. Just say apply there and open file. It's not encouraging. No, but this is why is it saying? Oh, all right, that's your spot. That's huh. Is it the one that you have on LUMI? Oh, that should be fine. And it does still look like the same thing here. Right.
Next time you hold this.
Yep. Small victories or silver linings or something. Well, let's see. Who is in? Yes. No? Okay. Well, I guess this will be unfortunately then just me showing what you can do with it, and then we can maybe workshop this in the afternoon a bit more. And yes, there is one modification to the host profile that was left here in the launch profile. So in the small and advanced, this should be Jan posted the path there. So it should be this path actually here. So our project path / visit. Starting to queue my small partition there. That will take a few seconds. Let's see if we can fix your thing. How's it looking? Okay, yeah, that looks good. Right, then when you click draw, it draws the plots. So that's like a...
So is it possible to have a breakout room? I don't think so. I'm trying to see what the issue with the SSH key and password is.
Yeah.
But I think a screen share would be useful here. Or do you want to take the screen share from on the main session now? Or are you in the room also? Ahmad Larity asking in the chat. I guess you're online only, right?
Yeah, I'm online, and I can go into a breakout room if you want.
Yeah, someone needs to set it up. I can't. Or do we handle it in the... building visit is very challenging. I've been doing it for over 10 years and I have lots of tricks and stuff. So I don't recommend trying to build it. What usually happens, in my opinion, in my experience, I'm answering to the next commenter, Sabrina. Usually I've been able to run the client version with older tools. So, and Debian and Ubuntu are kind of intercompatible. So
yeah.
Try your luck with installing one of those. Usually they've run most of them also on more recent
So
Linuxes.
Jan, there is now a breakout room as well, or two of them.
Okay, I'll go there. So if people online have issues, feel free to join us there and I'll see. Yeah. I'll go into room number 1. There seems to be 2.
It also seems like that there is the partitions are pretty full because I am not getting a compute engine from the queue. So this is going swimmingly. Yes, waiting for 32 cores for 1 hour, and this is constrained by priority. Oh, I'm slotted for 12. So okay, maybe that will start soon. Yep. No, I think that should go forward soon. Just a matter of minutes. And you have done something. You have a contour block of HE blocks. So yeah, here are like view options. You can reset the view from these. That might help. Okay. So now you have a bunch of contours of this variable that you have plotted. Double clicking on the contour lets you define those contours as well. Do I have a compute engine? Okay. That's not my computer. Let's go here. Is this now online? Engine. Yes, I have an engine. So let's see what I can do here. So demonstration. I'll just ping Jan to tell the people in the breakout room. Right. So I have now this Mercury simulation here shown or at least opened. So I can start plotting things. And usually we do use the pseudo-color plot because that's most flexible. There are others like the contour plot that was being used there. So now we have a plot of the 0 time state here of the proton density. So this is the initial state. This is a 5D run, so it's a equatorial plane. Yeah, I pinged Jan on this. Yeah. Well, I'm saying that to Jan as well. And yeah, this is probably a bit of an overkill to use visit for a 2D run. But if we zoom in, we can kind of see that this slab has a thickness because the simulation is 3-dimensional. It just has one layer of cells in this direction. And yeah, here we can reset our view to some default values and so on. But if we then use the time slider to get rid of this initial condition with the showing just the inner boundary of the planet there, then we can start to see how the simulation develops. And then we can also see that there's a foreshock from the proton data density moment. What did I have planned? I'm trying to follow my own thing here. So we can inspect a bit of the simulation specific things. So we can change here to BG boundary type. So this will tell us then like where are the boundaries of the simulation boundary conditions. So the side walls inflow boundary and the inner boundary, and then there are some do not compute cells there in the middle. And if we want to discard some cells here, we can do a selection, adding these operators to use some conditions to select things. Here, let's put the boundary type as a condition, and that was number 1 was kind of the computation domain for the Vlasiator solver. So let's apply that, and then we draw this again. And then we now have an empty hole in the middle where the inner boundary is. So we can get rid of that, and that can be very handy in 3D simulations. and because now we have this some thick slab there, we might actually want to do this as a 2D slice. So this is now just making it a bit prettier, slicing it along the z equals 0 plane. And then, well, it's not very exciting plot. We can change the variable to be again the, let's say, proton density. And we can have the Forshock there. Also, it's good to have this slice so you can plot, overplot some things like, let's say, a vector of the magnetic field. So this will be like a glyph plot. So it will insert small arrows there. However, this is scaling the data by magnitude, which is the vector magnitude is quite small compared to the one in the center of the dipole. So we disable that scaling, and then we can find the magnetic field vectors all over the simulation domain. And we can here indeed see that the Forshock is aligned with the magnetic field in the upstream, which is what we expect. Then, as for the velocity distribution functions, we can see from one specific variable here, like where these VDFs are being saved, and it is this sort of a sparse grid. Let's zoom in a bit so you can see perhaps see the cells there. So the red dots with the value flag 1 means that we have a VDF stored there. But this doesn't really help us now because we don't have any background on which to observe this. So let's put the density back there, back on the background slice. And let's add another pseudo-color plot and use this selection tool to flag these things. Selection and threshold. And let's now keep the default value there. So it will be using the plotted variable as the threshold, and we want cells with 1. And then we have these small cubes here on top of the slice. And we can actually go and do this sort of a pick operation. There's a selection of these tools. So we can actually go and click on one of these pixels. Right. So this will now display us the coordinates of this and the value of this variable that we just picked, but that's well, that's 1, so that's not very helpful. But what we want to see here is the cell ID. Let's add that there to the menu and apply, and let's click again on this guy. Now there's the output that we have a cell ID here equaling to something 300,000. Now with this knowledge, we can feed this into the Python package or the VLSP extract tool and so on. And that's what's the next demo being told in here. Let's do that. I'll add a new window to plot into, and I will open this extracted file. The path is given there in the examples. It's this sort of a velocity grid file format. It's not exactly the one I clicked on, but it's in the Forshock as well. And let's add the only variable stored there, so proton. And this will plot the whole of the sparse velocity mesh now. like so. And well, we might want to have a look inside. So there's the slicing operators. 3 slice is pretty handy. This does axis aligned slicing. And we have this sort of a, well, axis aligned slices here. Let's maybe adjust this color scale for the pseudocolor a bit. Let's constrain ourselves to the sparsity limit. And we have something like this. So we can see that there's this Maxwellian population here, and then we have this very wavy force-up beaming population here. But this is still very blocky. We can see this 4x4x4 block structure of the data structure here. So we can also here adjust operators to select based on the threshold. Let's say 1a minus 15 and draw. And well, now it's much smoother on the outside, and then the clips are there doing something weird. But let's get rid of the 3 slice and see the kind of the wobblier outer surface of this population now. So Maxwellian core, and then we see all these wobbles here nicely on the edge. But of course the edges are not maybe the most interesting part. So if we lower this bound a bit, constrain ourselves to higher densities, then we can start to peel off a bit of this distribution. And we see these interesting arcs, for example, there. Let's go up further. And now that's like a very small dense core there. I can maybe note at this point that we can do this slicing with isosurfaces as well. And we can select here some values, let's say 5 levels, starting from this threshold. Let's apply and draw, and then we should have a bunch of these. A bit smoother looking lines. And we can also do this so that we have a ramp in the opacity, so we can fade the outer regions a bit. So now we have this very interesting overview of the structure of this VDF. This is what our velocity distributions can look like, and if you indeed start to fit the Maxwellian population here, then it's you can see that it's not going to work very well, which is a point that we often make. Then we have a 3D run here as an example dataset. I'll do another window for that. And it's in the example data directory, EGE. And this is one of these smaller test cases, not quite science quality. Let's do a 3 slice of the proton density. And the initial condition is again a bit boring. But we can step forward and see how it starts to develop with some mesh refinement there showing up. Since it's a density type variable, and then if we have a flow going in from, or well, if we have high density at higher, at like a thin layer in a high resolution mesh, and if that flows into a coarse resolution mesh, then the mass is going to be spread over a larger box. So that explains these sorts of artifacts here. I'll just jump to the end of this thing, and we can see how there's a bow shock forming and a magnetopause here, and all the good stuff here. There's seems to be like a little FTE going there, like density getting piled up there and not being quite ejected. Let's see, there's few time states at 1 second cadence at the end here. Let's see if it's moving at all. And that's jumping a bit further down. It looks to be pretty stable. That's interesting. We have actually seen a case where we have had a flux transfer plasmoid starting to pile up on the day side, and it just wouldn't go away because the setup was symmetric and there's no noise, so there was not enough random wiggles to actually get this FTE pushed off of the nose, and we had to actually abort that run because that was just getting stuck on that portion. Last demo here, I'll just draw some field lines. Field lines tracing is done through this sort of an integral curve system, which is a bit convoluted in visit, but very usable. So it's adding a plot and then going to operators integral curve, and then we choose the volumetric magnetic field. And going to the integral curve settings, we can select some seed region. So let's take a sphere with some radius and some maybe not quite that many samples, but some, and let's trace both ways and apply, save the settings of that and draw. We get some warnings because we are propagating things also in the inner boundary. But then we have this magnetic field line structure here. Let's maybe hide the tree slice so we can appreciate the magnetosphere here. And you can see some reconnecting field lines here, or reconnected. So field lines that have just been reconnecting on the day side, connected to the solar wind here, and from the other side to the inner boundary. And a bit more on here on the flank, it seems. So that's interesting. And probably we could find some reconnection in the tail here as well, since it is driven such. Right. So this was then a very quick run through of what we can do with Visit. And well, hopefully at least some of you managed to get the software working and maybe able to follow along on this run through. And let's see if we can find some solutions in the afternoon for Windows machines and so. All right. Do you have now questions on using Visit besides the problems with Windows? There were some solutions for Macs shown there.
Yeah, so Marco, we have at least 2 Mac users who managed to point to their SSH key now, but then it says that it doesn't talk back to the MD server. But that the MD server did manage to talk back. I'm not sure what to try from the Mac side. We'll have Marcus online in the afternoon, and he's a Mac user. He will maybe have more tips. I know that from the Linux side, sometimes launching Visit with the -no-pty command option helps, or sometimes we've had one machine, not LUMI, but one machine only worked if we had the -debug1 flag set. But so Visit is open source and comes with some issues sometimes, but we'll try our best to get as many as you on with this.
Yeah, we have one question in the room here. If you, Jan.
Yeah.
That's a good point. There was this one edit that to be done in the host profile that Jan pointed out there, and it's in the HackMD. So I'll show it again here. Options. It's the correct host. Correct project number is here. Like this, it's this host settings, launch profiles, and then the small project here. So that's it's this, and the project number should be changed, and then visit install should be visit. And I will save that setting and actually push that new XML file there.
Technologically, this is a lot simpler than dealing with remote microphones and screen sharing and everything from a major lecture hall. So sorry to not be able to be there in person, but let's see about something maybe a bit simpler for plotting purposes rather than all that cool visit stuff that you were shown. Let's see, yeah. So data analysis using Analysator. Let's see, I've got some old outline here. Actually, we'll just pretty much jump into Analysator. I think I might want to go through a little bit of something, but let's see. So information, you've got the pages for this course. I updated them about 10 minutes ago with the final exercise. I don't have anything currently in HackMD for exercises, but let's use that for questions, because even if we do breakout rooms, then it'll be easy to copy paste questions and commands in there, and then we can trial them, and everyone gets the information that comes out of it. We do have also an Analysator wiki page, which is in various states of outdatedness, but there have been various attempts to bring it up to date. I think these pages that we are now building will be the next iteration and hopefully a bit easier to read. And you might also want to refer to the Vlasiator wiki or the Vlasiator outputs pages on the course documentation. So to, I suppose, recap, the Vlasiator simulations are large. So a bulk data file can be 5 to 40 gigabytes in size, and a restart file or checkpoint file can easily be several terabytes. So that means that we are usually storing our data files on compute clusters. You can download single files to a local machine depending on your hard disk size, but usually it is worth doing data analysis directly on the cluster. So the visit client server interface is one approach to that, but the other one is simply to run Analysator on the cluster itself, either interactively or in batch mode. Part of what is contained in Analysator is sidecar files, which are something that Markku has built and I have never even interacted with. But that can help if you need to generate smaller data sets, like a cropped region of the simulation data, or create new post-processing variables. And you can use those. I'll just verify nothing in the chat. So the VLSV files, we've got the visit plugin for reading these into visit, but we also have direct reading functionality in Analysator. And the data has a lot of binary data in it, and then there's an XML footer at the end of the file, which contains all the information on how to read it. And it is human readable, the footer. So sometimes it can be useful to just do a tail command on the file to see if the footer exists. If you don't get the footer there, then you know that the file is corrupt and there's going to be no way to read it into any of our analysis routines. But there also exists then Python routines for analyzing the footer data. Something to remember is that each VLSV file contains just a single time snapshot from the simulation. Some of our routines do have some workarounds for this, that you can access several points of data, but usually they're built that they open one VLSV file, read that, plot that, provide it for your analysis. And something that you didn't need to worry about in Visit, but might need to worry about in Analysator, is that the data inside the file is not sorted in coordinate order. So when Vlasiator runs on several MPI tasks, it decomposes the spatial domain both on the Vlasiator grid and on the FS grid. And when it comes time to output data, instead of writing small chunks so that it would all end up being neatly ordered, what Vlasiator does is that each MPI task gets its own part of the file, and then it just blurts out all the data into that, and it is the job of post-processing to reorganize it into the correct shape. So, of the output files, the bulk files, which are what we usually look at, contain parameters. So that is like the grid size, the time step, the simulation time. They contain Vlasiator grid data. This is accessed via cell ID values, and this can be a refined mesh. So if you've got a cell ID, then that cell ID will always be in the simulation at the same spot, unless it gets refined or unrefined. And then you can try to access the parents or children of that cell ID. It will be in potentially different parts of the file depending on how the data is decomposed to the MPI tasks. And the field solver grid, it's used for storing magnetic and electric field variables, but also could be used for storing, for example, moments which are communicated and used in solving the magnetic and electric fields. It's a uniform Cartesian non-refined grid, which means that if you have a large 6-dimensional simulation, the FS grid also gets really large. You can be talking about 2 gigabytes per single variable, which means that we actually don't usually store it. But especially if you're working with 5D simulations, then go wild, store the FS grid data. It will take the exact same amount of space as the non-refined 2D Vlasiator grid data. And we also have the ionospheric grid, which is this triangular static refined mesh of ionospheric values. We also have a tool for plotting that, and we can plot velocity distribution functions, which are stored for certain of those cells. So an example, this is from Analysator, a Vlasiator grid plot, where we've got the cell IDs, which have been, cell IDs start from 1, and they have been reordered into this plot. So that we can actually see them in order on screen. Cell IDs, they start from the lower left corner and increment first along X and Y and Z. They start from 1, not 0. And so on the 0th level of refinement, you will have NX times NY times NZ cell IDs. The next refinement level increments the subsequent cell IDs. So we start from what we have received on lower refinement levels, and then the next one going to 8 to the power of the refinement level. And then the cell IDs either exist or don't. Because if you have a cell which still remains on the lowest refinement level, then the children of that cell will not exist, and their cell IDs will not exist in the simulation. Whereas then, for example, here in the center regions where we've got something interesting going on, those cells will have been refined. So then the lower level cell IDs will not exist, but the higher level cell IDs will exist. And this means that as a very, very important piece of metadata, we actually store for each VLSV file the list of cell IDs active in that VLSV file. And that can be used to reorder the data as necessary. So we can see that this is Vlasov grid values. We've got proton z-directional velocity, and you've got the low resolution cells, really low resolution here out at the edges, and then medium resolution and higher resolution here towards the day side magnetopause region. This is EGE, so it's the quite coarse file that we've used for early testing, and I believe that's also what we'll be using here for these exercises. And the FS grid. So FS grid does not use cell IDs because all of the cells always exist. It is a simple uniform Cartesian mesh. So you can build connections between cell IDs and FS grid indices, and we actually do have kind of an internal FS grid cell ID, which does get stored if you're storing FS grid data, but it's not something that's really actually shown to the end user. What we can see here is that since all the cells are the same size, we have a uniform resolution everywhere, but you can still see effects that stem from the Vlasov grid resolution. For example, here you can clearly see that there's rectangular regions where there's been a moment that has come from the Vlasov grid, has been mapped to the field solver grid, and has been used to advect the fields, and has caused some chunkiness. So this is an old simulation. It does not include filtering to get rid of this chunkiness. If you generate new simulation files, there will be filtering active, and you won't see it at least to nearly the same effect. But you might still, if you turn the filtering off, or if there's adaptive refinement, then you might see some small effects to that degree. The ionospheric grid, I don't have a picture of the actual mesh of the ionospheric grid. It's refined according to parameters in the config file so that you get good resolution near the regions of interest. We have a couple of simple 2D plotting tools for one hemisphere at a time analysis. But of course, you can only plot these if you are running a 6-dimensional magnetospheric simulation with the ionosphere in a boundary active. And finally, the velocity distribution functions, which in restart or checkpoint files will exist at every single cell ID, are stored for only certain cell IDs in bulk files, because of course they take up a lot of space. We don't want to store 5 terabytes of data for every single simulation time step. There will be one distribution function per cell ID and per population of particles. So if you're running multipop, for example, protons and alpha particles, then you'll have 2 VDFs in the same cell. And this is a Cartesian uniform 3D mesh, but with sparsity. So the maximum extent is defined in the configuration file, and you can set the sparsity threshold, and anything that is above the sparsity threshold will be included and everything else excluded. And the analyzer plotting tools include methodology to take this velocity distribution function, which once again is in a completely potentially weird organization on disk. They are not in any way guaranteed to be in contiguous order, or rather not in order, they are contiguous. But then that will reorder all of this data so that it can be plotted. And because it is a 3D velocity distribution function for one spatial location, it means that if you want to do a regular 2D plot, then that can be either a cut or a slice through the distribution function, or you can project it all to a plane. So this is actually an old picture which has an error there in the units that has since been fixed. So let's have a look at Analysator itself. Analysator is the name of the GitHub repo, which has data extraction, data analysis, data plotting, data post-processing, and through those sidecars also you can write new data files. One of the most useful tools, which people always forget about, is that it includes command line help. So first, if we import Analysator, due to historic reasons, it is actually called PyTools, and we have considered renaming the name of the Python module to Analysator, but that would mean that every single script that anyone was ever using would need to be rewritten. So we haven't bothered. But then we usually import it simply as PT, because why not? Inside it, there's some substructure. So we have, for example, the VLSV file substructure, which includes objects like the VLSV reader. So if you're using interactive Python, you can type pytools or pt.vlsvfile.vlsv reader and a question mark at the end and launch that command. And this will give you some basic documentation about the object or function. So this is a class for reading VLSV files. It will initialize the VLSV file object. It'll open it. It'll read the file footer, read in some parameters, do some preparatory data, caching, that sort of stuff. So for this one, there's actually not a lot of information. But then if you were to type dot and read variable info, for example, which is one of the accessor functions, and use a question mark there, then that should give you up-to-date information on what the function does, what its inputs are, what its outputs are. And if the information is not up to date, please let us know and we will fix it. A brief overview of what actually is included in the Analysator repository. Documentation is severely outdated. Don't look in there. There's some example routines. Those should be mostly up to date. We've got calculations, so post-processing scripts, subplotting routines as examples. Then we have another outdated thing, which is the MayaV interactive 3D plotting interface, which has its benefits, but has a huge amount of prerequisite Python modules and installations. So having that installed on a local laptop is really no issue. You can install it and you can try using it, but you running Python and Analysator on a supercomputing cluster, getting MayaV there can be a real pain in the neck. So it's actually turned off by default and it's not being updated anymore. If you want to do 3D plotting, just use Visit. It'll be much better. Then we've got the PyPlots subdirectory, and that is where all our modern plotting routines are housed. That's the basic place where you can look into what's available. Then we've got a directory for the VLSV file interaction routines, or the reader and write scripts. Then there's, we really should clean up the structure a bit. There's a directory called script, which has helper scripts, stuff like calculating spectrograms, some of it very much under development. There exists a test package testing suite. This is inspired by what we have for Vlasiator itself. The idea was that when we change some functionality, we can bulk generate a huge amount of images to test how all of the various output keywords interact and whether they still make sane images. Then there's a tools subdirectory, which has, for example, the VLSV intpol script, which is the canonical method for creating virtual spacecraft, also quite dated. So it can be used as inspiration, perhaps more than actual direct use. And we do have some cleanup. So there is a trash can where scripts go to die, but we should move quite a bit more stuff there. So inspired by this training event, maybe we will clean up the Analysator repo a bit. And then there's some base information files, file management, and the main file that gets imported into Python. But so if you want to learn about what kind of things may be possible, then you can always just browse through the repo, and specifically the PyPlots and the scripts folders are those ones which contain a bit more useful stuff. And then today we will mostly be focusing on something approachable, so ready-made included plotting scripts. In the PyPlot directory, we've got the importing file, which just is used to pull in everything else. We have a plot color map, which does 2D color map plots from 2D simulations. Now that we have 3D simulations, we can do a slice from a 3D simulation, so that is called color map 3D slice. We also can plot isosurfaces and so-called 3 slices. Then we have plot helpers, which include some helper routines like vector operations, Jacobians, that sort of stuff that are required, that are then used by the other plotting routines. Plot variables is a very old unsupported miniscript for 2D plots and should be probably trashed. And then we have plot VDF, which is used to visualize these distribution functions. So 2D projections or 2D slices of VDFs at a single cell ID. And finally, there's VDF profiles, which plots Cartesian profiles over a VDF. And that is really designed just for debugging purposes. You probably don't want to delve into that too much. Now, if you want to do actual science with Vlasiator, these will probably not be enough for you. You will need to actually extract the data and rejig it yourself. But existing scripts can be a good starting point. And when you're running Vlasiator and want to see how the results look like, what does the simulation look like, these are your tools for that in addition to Visit. So a few quick examples. We are using pt.plot.plot color map. So this is a 2D script. And for that, we are feeding it in. There's example data AGD bulk file 900. Actually, that should be 904, I think. I've got the, yes, I've got the old command there. So what we have here is what it does by default. When you just give it a file name to a VLSV file, it will plot the 2D domain that it finds. It will read in the metadata and figure out what are the dimensions of this 2D file. If it's a 3D simulation file, it will throw you an error and say that you're using the wrong script. You can see that it automatically defaults to using Earth radii as the X and Y axes, because that is the unit that we usually discuss. It defaults to plotting the proton number density in units protons per cubic meter, because that is the internal Vlasiator unit. It gives you the simulation time, and it defaults to a logarithmic scale. So if it gets a scalar, it'll default to a logarithmic scale. It takes the minimum and maximum values from the simulation data. It masks the inner boundary region out and uses this hot desaturated color map so that it sort of makes some details jump out. You can switch to other color maps, of course. So this is the default that takes place if you just give it a VLSV file. But what can be done is we can look at other interesting stuff. For example, here from the same file, except again, we've got the wrong time step there. We are plotting the VGE grad PE variable. So it's on the Vlasov grid, and it is an electric field value, and it is the gradient of the electron pressure gradient, the electron pressure gradient term that goes into the electric field. What we've got here is we've additionally given it the draw equals 1 keyword. So the way that analysator plotting routines have been built is that you give them keywords. They always have some default value so that we can just give it a VLSV file and it'll be happy and plot something, but then you can change the defaults to something else. By default, it actually saves to disk a PNG file. If you want to plot interactively, you need to tell it to draw to screen instead. Except if you are running it inside a Jupyter notebook, that backend defaults to also showing it on screen, even if you create a PNG image. So here, when we didn't give any keywords, we just gave it the file name and that's it. It said, okay, I'm finding the proton population using that. And it said that it saved this file name into that directory. But it also gave me the image because I was using Jupyter Notebooks. But here, since we say draw equals 1, that could just as well be save equals false, but that's the one that we now have, then it will no longer try to save to disk. The other stuff that we've done here is, apart from setting the variable, we have set the scaling factor. So because Vlasiator uses SI units internally, then the electric field will be volts per meter. But these values are very small, so we scale them up by 1e3, which means that the unit becomes millivolts per meter. And it is reflected here in the color bar title. We've set the minimum value to 1e minus 3, as you can see here. That means that we actually have these white dots here are zeros. And you might wonder, why does this look so weird and grainy? And that is because we are actually looking at what the simulation has calculated for the electron pressure gradient term at that position. And internally, we use slope limiters, which enforces good behavior whenever there's a shock front, for example, or discontinuity. It reduces diffusion quite a bit. But what it also does is that the gradient becomes 0 if you have a minima or maxima point, even if it is only barely a minima or maxima. So all of those values have gone to 0, but we've masked them out so that we can actually use a logarithmic scale here, because of course you can't take a logarithm of 0. And additionally, we have set the color map to Viridis, which is one of these fancy new perceptually uniform color maps, and is a bit more scientific than good old hot desaturated. So this is not an error that it has this stuff. It's just that you are actually plotting a variable which has values of 0 in many places. These regions here are the undisturbed solar wind, so we are looking basically at numerical noise, which sometimes gets these minima maxima, which lead to the gradient being 0 after a slope limiter. Okay. What about 3D then? 3D is the future. This is now the EGE simulation that you have access to a couple of files of. So low resolution, but 3D simulation or 6D simulation. Again, this test here just takes the plot color map 3D slice function, gives it a file name and nothing else. Once again, we see that it finds the proton population and it saves the image as that PNG file, but also we've got the display through Jupyter Hub. We again see proton number density. We see the X and Z axes. These are the defaults for magnetospheric simulations, because then we get the pretty cusps and so on. We get the tail current sheet, which we often want to look at. And we see the cut point, which is y equals 0 in the center point of the simulation, going through that. And we also have the time. So now these are the basic values which tell us what we are plotting and from where. Again, the color bar defaults to logarithmic with the hot desaturated color map. And the minimum and maximum values have been inferred from the actual simulation data, and the inner boundary region has been masked out. Okay, what can we do to change what we are seeing from the simulation? Well, here we have quite a bit of stuff that we've thrown at it now. We still give it the file name. We can define the normal direction manually. So we've got some copy-paste error there. Of course, if the normal direction is Y, then it should be the same hyphen on both sides of it. So Y is the default, so that we get the XZ simulation plain visible, but you could give the normal direction as X or Z as well. Sadly, in its current form, color map 3D slice does not support tilted slices. They have to be in the Cartesian direction. The reconstruction will be getting quite a bit uglier if we had to do diagonal slices. We said draw to 1 so that we're not saving a PNG file. We are turning off scientific notation. So I'll just jump back to the previous slide, and you can see that here, when we have proton number density in units of protons per cubic meter, we actually have 1.0 times 10 to the power of 6, so scientific notation. And if you turn it off, then you get regular numbers, regular notation. We have done rescaling. And actually, let's jump down to here where the variable is, for protons, the velocity on the Vlasov grid. So our units, let's see. I think I have a mistake here. It is possible to make mistakes so the units by default are meters per second for velocities, but I have used v-scale 1e minus 3, which means that we are dividing the values by 1,000, which gives us actually kilometers per second. But instead of allowing the color bar to have the default title, which would reflect that and be then VZ kilometers per second, I have for some reason overridden it with the incorrect unit. So yes, it is possible to tell the script what to do, even if that would then be incorrect. Whoopsie daisy. Then we have keyword symmetric. So especially if we are looking at something which is a component. So here we have the operator Z. So we are taking the Z directional component of the velocity. Then we get a diverging color scale, which is linear by default whenever we take a component. And here, when we've decided to also add the symmetric value to 1, that means that it will see what is the largest value and what is the smallest value, and set the scale so that it is symmetric around 0 and encompasses all values within the plot. We've added a title manually, EGE, and have chopped out the time, but so we can manually alter the title and the color bar title, where we've now lost information about the time and we've got incorrect units, so be careful. And as you can already see, we are zoomed into the simulation. We have supplied a box in units of Earth radii, which is first 2 are the X values and the second 2 are the Z values if we are doing an XZ plot. So minus 25 to 30 and minus 25 to 25. We have zoomed in closer to the inner region to get a bit of extra detail. We have added the Earth equals 1 keyword, which draws this symbol at the center at the correct size of what the Earth is. So this is a good reminder of our inner boundary being actually a bit further out than we would like. And the Earth is actually inside there. And we've also added vectors. So we've got the color map is the Z directional proton velocity. So it's coming in from the solar wind. We've got Z directional velocities of 0. It's just pure X directional solar wind. And then the flows diverge here at the nose into the northern and into the southern magnetosheaths. You've also got some flows inside the magnetosphere there. And then they loop down and you've got southern flows in the northern lobe and northern flows in the southern lobe. And the vectors actually show us that as well. By default, the vectors give the vector gives the direction and the color of the vector gives the magnitude. So this is just, a subset of various things that you can tell a color map 3D slice to do. Let's see, here we have, this is also from EGE, normal is again Y, but what we've now done is we've scaled using 1E9, and the variable is the FS grid variable magnetic field. So this file does have the FS grid variables. So using the scaling, we go from Tesla to nanotesla in units. And again, we've manually overridden it, but we wouldn't actually need to do. It's just that if you don't override it, then it will contain information here about whether it's a Vlasov grid or a field solver grid variable. So if you're doing publication-ready images, then you might at the final stage want to override the titles and clean them up a bit, give less information if so you wanted. I actually have no idea why the symmetric keyword is that. It doesn't do anything because we are plotting logarithmically. So you can give it commands and it will ignore some of them. We've again done the zoom in, and here we also get some output from the FS grid decomposition. So it tries to read it from the file, can't find it, calculates it instead in post-processing and figures it out. And we've got some debug information there because this is something that we fixed recently. We had some issues with the decomposition being a bit ill-defined in certain cases, but now it should all be fine and dandy. We can also then overplot other information. In the previous plot, we had vectors, but what we can also do is we can set the keyword F saved. So distribution functions, F, are saved and made visible. And this will overplot a contour, a black contour for all of those cells which have distribution functions. Now this is from the 5D simulation, and it's actually quite fun. You can see that each of these little black dots is a contour around the spatial cell. So the resolution of the simulation is quite decent here. And we have our usual striding grid, which takes, for example, the every 25th or every 10th cell and stores the VDFs there. But we can also see that you can set these spherical shells or rings around the origin where you can get a much greater density of VDF saved. For example, if you were inclined to look at something close to the bow shock, like SLAMS formation, then this would be a very useful tool to get VDF saved where you really want them, instead of using up huge amounts of disk space and trying to store everything. Then you want to look at the actual VDFs. So the command is pt.plot.plotVDF. You give it the file name. You tell it to draw instead of only saving to disk. And then we have a couple of different options. One is to directly give it a cell ID, which can be a bit faster. And if you're like doing scripting over a number of cells, it might be useful to have the cell ID stored so that you can plot the VDF for that. And then you can also pull out, for example, loss of grid vector or scalar variables for that cell. But what we've done here is we've given it the coordinates in Earth radii. So X coordinate, Y coordinate, Z coordinate. What it does is that it will look at those coordinates and find the closest spatial cell that does contain a VDF and give you that. We've set C bulk. You could just as well say center equals bulk, which transforms the VDF into a frame of reference centered on the bulk velocity, which we can see here that we've got the blob mostly centered at Z and X velocities equal 0. We've decided that we want the XZ plane by XZ equals 1. You can choose any of the Cartesian planes. And the VDF plotting is a lot more verbose. It will give you that we are reducing the V-space by integration. So we are flattening it instead of taking a slice. Those coordinates gave us the nearest spatial cell at these coordinates and nearest V-space there. Unique cells with V-space probably is 1. We get the cell ID information and the coordinates. We transform to the plasma frame. So C bulk, transformation to plasma frame. It gives them information about the velocity space, how many velocity space cells were found. This is a nice heuristic that in that one point of the simulation that we are now plotting, we had 1.4 million velocity space cells, so sampling points of the distribution function. And we found the sparsity threshold in the VLSV file. Sometimes for older data, it might not be there. It can also be overridden manually. But that defines the edge of what we plot, because the actual information on disk also contains buffer regions going beyond this sparsity contour. But what we can do is we can actually ignore those because this is what we are sort of certain about scientifically. And that actually is not performing a slice. That is outdated information. We need to clean that out because it's doing the integration. And it gives us what is our active F range here in these proper slice units. So we can then give various different keywords. We can change the coordinates to look at a different kind of cell. We can center at the peak value of the distribution function instead of the bulk value. And we can also rotate the distribution function. So for example, here we have given the keyword b para 1 equals 1. So we get the x-axis is velocity along the magnetic field in that cell, and the y-axis is velocity along a direction, which is the b cross v direction. So there exist keywords for all 3 slices along this standard notation rotation direction. There's a bunch of other keywords also available for plot VDFs, but I'm not going to go into those in detail here. Then plotting 3D simulations, it is also possible to do these 3-slice plots with Analysator. So here what we've done is, again, plot 3 slices, the function name, you give it the VLSV file, and then we've given draw1 so that it doesn't try to save it to disk. If you don't give it a cut point, it will default to the origin, which makes sense for magnetospheric simulations. And once again, we have defaults of proton number density, logarithmic scale, hot desaturated color map, time, origin, and because now we don't have regular axes and we have information here that we have ticks every 10 Earth radii. And this is a bit slower. I think doing this plot took like 40 seconds because it actually has to construct it from 12 different plots. It does these slices. If you are running it in a suitable Jupyter environment, you can also run it with an interactive plotting backend, so you can drag and rotate. But mind you, that can also be a bit sluggish. But if you are having lots of trouble with Visit, then this is always an option. Keywords that can be given include like leaving out some of these plot planes, defining the rotation, all the regular stuff about which variables, what color maps, how to adjust the color map axis. All of those are available here as well, or at least most of them. So this is now a demo of the interactive backend from a different computer. So it's an animation. And you can see that I drag and it thinks a bit and then it redraws. So Visit can be a lot nicer if you really want to do interactive plotting, but this is also one option if Visit is really being problematic. I have not been able to make interactive plotting available on the LUMI Jupyter interface, so I'm afraid that is not possible today. That's it for the actual presentation. And next, I would suggest that you go to the course website where we've got the documentation. There's introduction on how to get a LUMI Jupyter notebook running. If you followed the pre-instructions about downloading Analysator to your home directory on LUMI, then using those instructions, you should be able to launch a Jupyter interface on a compute node and just start trialing it out. There's also a lot of sample commands. What you can do is, for example, you can create a VLSV object, there's instructions there, and you can list from that object which variables it includes. And then you can give those to the plotting routines. The plotting routines do support tab completion for keywords, but of course, if you're giving the keyword a value of which variable you want to plot, that is not supported. So you do need to know which variables are included in the VLSV file so you can tell it what to plot. Okay, so I suggest you give it a go. There's the ionospheric plot files, VLSP files. There's 2D simulation files, 3D simulation files, and all of those, or at least the 2D and 3D, should include VDF. So you can also try plotting those from different parts of the simulation using those keywords. If you find errors in the documentation, please let us know and we will fix them ASAP. You can also use the HackMD to ask questions, and I think we'll do breakout rooms as well. How's that sound?
All right. Thank you, Marcus, for this talk.
On LUMI, you can run it on any machine that runs Python and has all the necessary libraries, but for the purposes of this course, you can run it on LUMI. So go to www.lumi.csc.fi, log in, and then you get the web interface. You've got a bunch of pinned apps here. You can go to Jupyter, not Jupyter for courses, but regular Jupyter. Then it gives you the opportunity of launching an interactive session. So here you select the project here, interactive partition, number of CPU cores for the job, because this will be running on a compute node. You want to up it up a bit, so maybe say 4 nodes or 6 nodes, depending on what sort of visualization you want to do. If you're going to visualize some of the larger 3D visualizations, then that memory use can really go up. Time limit, yes. Working directory is the default. Now this remembers my previous settings. So you can either have basic or you can go to advanced. And I suggest you go to advanced, custom init text, and these instructions are in the analysator introduction. So you need to put these, just copy paste them into here, and the important thing is to also have the semicolon here after the path to your analysator directory. So this assumes that you've done the prerequisite, which is cloning analysator into your home directory on LUMI. I'm not going to do that now. I already have it there. Then you click on launch. The PT no LaTeX is, it turns off the advanced LaTeX text handling of analysator. Matplotlib does a fair amount of fancy text handling and markdown, but we've built it so that you can actually run the text live interpreter to properly generate texts for your plots, but it can be turned off with this. And there's no text live on LUMI, so we need to turn it off. So we launch, and this page collects a list of old closed instances at the bottom. So now I've just got this one here, 1 node, 8 cores. It is starting. We need to wait for a little bit until it gets all the modules loaded and launches the Jupyter host, and then we can connect to it. So meanwhile, let's see, we've got this is actually Marcus version, but should be up to date with the regular ENCCS version. So analysator exercises. We've got boilerplate text there, and then we introduce with a couple of VLSV reader files. Okay, this has started, so I will connect to Jupyter. It opens a new tab, and it'll actually show my old history from my previous notebook, but I will start a new one for the purposes of this. Once it loads, it can take a while. So, new Python kernel. So, first things first, import PyTools as PT. So in Jupyter, you type command into a command window. With enter, you can add several lines of code, and it executes with shift enter. And you get an asterisk indicating that it's running, and once it's completed, you get the history item number. So it tells us it's using the inline plotting backend and Matplotlib version 3.8.1. It doesn't give you detailed information about the other modules that it loads as part of it. You need Matplotlib, NumPy, SciPy, maybe something else, but we've tried to keep it pretty simple so that they should be runnable on a multitude of different machines. Okay, then next commands here are 3 different VLSP reader objects where we create a 2D object, a 3D object, and the ionospheric object with the paths to the files. So I'll just launch them there. And for each of those, it finds a population proton. That's one of the standard boilerplate texts when you create a VLSP object. Then we can list the available variables. So that is, from a VLSP object, you can list. Then you can also list available operators and available data reducers. Let's start off with f2d.list. It shows that we get, we've got a number of parameters. Now, a parameter is something that exists only once per VLSP file. It's the time, when in the simulation was this file saved, what was the simulation time step length at that point, what was the time step, as in integer, how many time steps had we done, what was our field solver subcycling, what was the file indexing, sizes, 0th reference level, cell counts, version, how many writing ranks we used for this VLSP file. This is used for the FS grid output. And if we have some of our more advanced data reducers, such as solar wind energy density or precipitation data, then the center energies for the bins are stored there. And these are some helper values for these as well. And also what was the loss cone angle that was used for the precipitation. Then we have a list of variables. Now this is the most important thing. So these are things that you could plot. We store the cell ID, which is the index into the simulation domain, and that is stored as a variable, but is then used actually to aid with all of the other variables, to sort them, all the loss of grid variables. Then we've got a list of field solver grid variables here. This is a 2D simulation, so we haven't been too careful about storing those. We've got magnetic field, the perturbed component of the magnetic field, boundary types, electric fields, all of the 12 different components of the Hall term for the electric field, maximum field solver time step, and which MPI rank handled each field solver grid value. And then we've got, I'll jump to the end, we've got some values on the Vlasiator grid. So we've got volumetric magnetic field interpolated to the cell centers. The boundary type, we've got electron pressure gradient term. VGF saved is this flag which indicates whether the cell at that location has the VDF saved or not. Load balance weight is the value used for decomposition with Zoltan. And then we've got just the scalar pressure and the MPI rank. And then we have these which are per population. Usually we run just protons, so we've got proton / VG, whatever. Blocks count is the numerical cost of that cell, how many blocks we are computing. What the effective sparsity threshold is, that is in case we are running with a dynamic threshold, which allows for a lower sparsity threshold if there's very little plasma in that cell in general. Energy density calculation, maximum time stepping for the acceleration and translation velocity solvers. Then we've got this indication between non-thermal and thermal parts of the population. So what we do here is, in the config file, we set what is the solar wind value. So what is the solar wind bulk velocity and what is the solar wind thermal velocity around that bulk velocity. Anything within a certain radius is considered the thermal part of the solar wind and will be reduced into these values. So density, velocity, and pressure. And then anything outside that will be in the non-thermal part. And we also get the pressure tensor, the density and the velocity reduced for those parts of the population. So, for example, in foreshock simulations, we can look at different parts of the population, but it's only valid where that parameterization is same. And then we've got the total precipitating differential flux. So this is a vector variable with a number of bins. I think here we might have, let's see, yeah, we've got 16 bins of precipitation. And then we've got the pressure tensor, the diagonal and the off-diagonal components. We can use those for example, a gyrotropy analysis. And then we've got proton density, number density, and then the rho loss adjust is a counter for how much number density we have thrown out due to sparsity. And then there's the proton population specific bulk velocity. So we could plot some of these. Let's actually do that. Plotting 2D, 5D simulation data. I will copy the center one of these so we can give the VLC file in different ways to the command. Let's scroll down here. Oops. And this will now give us the standard. So it was saved into that file name. We've got the time step, proton number density, logarithmic scale, etc., etc. But let's now try to plot something a bit more interesting. So let's say variable is proton BGV. So now this will take the proton bulk velocity and reduce it to its magnitude because we didn't give it an operator. And we can see that it is mostly uniform throughout the incoming solar wind. And then we've got actually an increase in magnitude of velocity here in the dayside magnetosheath, and then decrease here inside the magnetosphere. But the logarithmic scale is perhaps not the best here. So let's switch to a linear scale. And that looks a bit more interesting. So we've got, you can see here there's a foreshock that has built up. So that actually is a reduced velocity because you have some backstreaming ions. And when you calculate all of them together, then the bulk flow velocity here is a bit smaller. And then you can see that there's now what appears as a slowdown here in the sheath. Okay. Let's say that instead of having the velocity in meters per second, we will now set V scale to none. So this is default value. No, not the default value. The default value is 1, but if we set it to none, it actually automatically chooses a suggested value, and that is kilometers per second. And here we have velocities going all the way down to 0, but this scientific notation is not terribly useful here, so we turn it off. You can often use 0 or false or none interchangeably, but not always. So here we go. Now we've got velocities going from 0 to 811.7. We've got very low velocities here in the inner domain. Let's try and see a bit more detail here. So we will push the minimum value to, let's say, 400 and the maximum value to 800. So we'll let it slightly saturate at the top end, but we'll get some nicer tick marks there, I think. Let's see. Oops, these are not nice tick marks. We're going from 400 to 800. So what would actually be a lot nicer would be, instead of having 7 tick marks, we want 5 tick marks. So we will change it there. Linear 5 tick marks. And hey presto, we've got 400 to 800 kilometers per second proton bulk velocity. There we go. Okay, so here we can see that there's increased velocity here at the edges where you've got backstreaming ions, and then you've got a lot of populations here, and then the sheath actually undersaturates here because it slows down to total velocity is much less than 400 kilometers per second. Now let's remove the maximum and minimum values and instead look at the x-directional component of the proton velocity. Oops, forgot that one. And we see that we've got values from minus 780 to plus 370 or so. Okay, let's assume that we would want to look at values close to the solar wind value, which was 750 in this simulation, I believe. So minus 775 and maximum minus 725. Let's see what this looks like. Aha. Now by choosing these values for the minimum and maximum, we have a white at 750 kilometers per second minus x directional speed, and that is indeed the solar wind speed. So we see that in these regions, the solar wind is undisturbed, travels at the regular solar wind inflow speed. And in these regions, it has slowed down. So we've got the red color, and then actually we do have some parts in the foreshock where the speed has increased. But this is sometimes a bit irritating that when using a linear scale, so that you get, you can do this minimum and maximum value around some white value. Well, okay, it's actually quite useful for this because we are going around a value which is 750. But let's now look at what do the magnetic field measurements look like. So we'll change the variable to FGB, and we'll let it automatically scale, and we will remove those values and actually that as well. Let's just look at what does the magnetic field auto-scaled look like. So we get nanotesla as the unit, that's the auto-scaling value. We've got values going from way less than 1 nanotesla. They're behind the magnetosphere, mostly around 5 nanotesla, which is, I think, our solar wind value here. And then we've got some enhancements and some rarifications in these waves. Let's look at components then. Operators, I previously used stuff like X, but this is an XY simulation domain. So let's look at the out of plane value. So that's the Z value. We can also just use the number, the component number 2 here. No, we can't. Oops. Let's go to that. I think maybe it's internally that it can do indexing. Well, here we go. Our out-of-plane component of the magnetic field doesn't look very interesting. The reason, of course, is that this is a magnetospheric simulation, so we have the Earth's unscaled dipole field here at the Earth, and close to the inner boundary, the magnitude is quite drastic. The scaling is 1 over distance cubed. So using a linear scale, which is the default for any component of a vector quantity, is not very helpful here. Now what we could do is we could manually adjust the linear scale. Let's try that. Minimum value would be, it says minus 16 there, so that gives us a guess. Let's say minus 17, and maximum is 17. Okay, this is looking quite a bit better. Now we can see that there are ultra-low frequency waves in the magnetic field component out of plane here in the foreshock, and then we've got stronger compressed waves here in magnetosheath, stuff going to the sides. But this is still a bit difficult to see here. And at the same time, it is very nice also to see the waves in the sheath. Now, we have the capability to use the symmetric logarithmic color scale. This is a replacement for the linear scale, and I'm setting symlog equals 0, which means that it can automatically scale the center region. So what it does is it has logarithmic regions at the top and the bottom, and centered at 0, and then it takes the center region, which is actually with a linear scale, so that it's even doable. So here we can see, okay, this is actually now drastically sort of oversaturating, so we can very clearly see that which are the regions where there is a positive or a negative Z component of the magnetic field. But it makes for a pretty picture. If we remove the default settings, the manually adjusted minimum and maximum values, we can see what it looks like. And okay, actually just allowing it to automatically decide the values looks quite decent. There's now a significant scale, logarithmic scale, using both the sheath and the foreshock. Okay, I was actually probably going into a bit, I was jumping a bit ahead here, but this is how the plotting works. So you've got then here in the instructions, you've got the basic plot properties. So remember to use the list to evaluate what you can plot. That gives the list of all the variables that exist in the VLSV file. And that depends really on the file, what the Vlasiator simulation decided to output. So if we do fiono.list, see, I'll minimize that one. No, I can't. Okay. We see that for the ionospheric VLSV file, we have a lot of ionospheric variables, but very few Vlasov grid variables, and only the electric field on the field solver grid. Then we had the option of also looking at operators. And this is just a reminder of what kind of operators you can give to Analysator. So you can take the magnitude of a vector, or you can take an absolute of a value. You can sum the components together. You can just try to parse it directly so a vector remains a vector, or you can take one of the components. And then the data reducer output flag is a bit more involved, gives quite a long list. These are not passed from the file. They are just what Analysator itself potentially knows about. So it can calculate, for example, a velocity based on the density times velocity and the density. This is, for example, used when plotting something from a restart file. You've got stuff like the magnetosonic speed, the sound speed, the alpha n speed, Mach numbers. You can calculate what is the velocity parallel to the magnetic field. So you've got all of these different reducers, and it then lists what values does it need to be able to run. And we have toyed with the idea of passing through this list and only returning those values which are supported by the file, but haven't got around to actually doing that yet. And you can see that none of these actually have the FG or the VG or the IG underscores. If I recall, let's see, let's use the auto completion here. I think we had something like this. Does it work? That's variable, no. Maybe it actually only plots the old ones. We'll have to look into that. Well, what you can also do is you can look inside the Analysator repo in the reducers file, and all of these are listed there as well. So you don't need to do the dot list operation. But the important thing is the dot list operation tells you what you have in the actual VLSV file. Let's see, what else could we do? We could plot the VG blocks. So this shows now the computational complexity of the simulation on a logarithmic scale. So this is one of the reasons why load balancing Vlasiator is challenging, that here we've got regions of the simulation where we have less than 1,000 blocks. So if that's 1,000, 900, 800, 700, 600, we've got like 400 blocks in these regions. And here in the magneto sheath, we are going to over 30,000 blocks. So a lot of dynamic range in the simulation. And I'm going to actually try, what does this do? Let's plot the cell ID. Ah, it works. And here you see that the cell IDs start from small values. Let's see. Let's give it a linear range. That's better. So we start from values 1 in the corner, and then they increase first with the x-axis always, and then with the y-axis. We get a nice rainbow color scheme. So this is just the cell IDs which have been then reordered according to the cell IDs. You can see what the ordering is like. Then let's see VG rank. So this is the MPI rank of the simulation. So you can see that this simulation was run with 360 MPI tasks, and they are distributed in quite an interesting manner, but mostly rectilinear blocks. We use the slightly more involved RIB scheme nowadays. It's better in 60 simulations. Okay, then we can alter the color scale. So if we go back to using cell ID, because it was a nice and uniform plot, let's change the color map. We have this one called Warhol, which is interesting. It really makes different regions pop out. So if we now decide to say proton, VG row non-thermal, if that is a name, if I remembered it correctly. Let's see what it looks like. Okay, let's plot that in a logarithmic scale instead. Should be more interesting, and we get something pretty psychedelic. So in these regions, the rho non-thermal is 0. There are no particles which fulfill that criteria, so they go to white. But then we can get some pretty amazing pictures. Right, something that my colleagues reminded me that when we make these fancy pictures, of course, we want to watermark them.
Yes.
So I will put a watermark in the top right-hand corner. And it complains about the rescaling. And okay, actually, it's slightly overlapping there. Let's put it in the top left-hand corner instead. And this way, you can easily create images that indicate that they are Vlasiator images. If for some reason you need a black and white watermark, then that is also possible. There we go. Excellent. Let's see. Let's also see what the VDFs were on this simulation, where they were saved. So I just added fsave1, and we get the contours indicating that we have this grid pattern overall in the simulation showing where cells were saved, and then we have these enhanced regions near the bow shock for this particular purpose. Let's zoom in a bit. So I will be going from 5 to 15 Earth radii. So we do an array, 5, 15, and 0 and 10. There we go. So this is the X extent and the Y extent. And we see now we've got some really psychedelic colors going on here because we're still using the Warhol color map. But you can see that there's the bow shock structure somewhere around here. And you've got all of these foreshock wibbles. And then we've got the contours. And you can see that actually with these circular regions, you sometimes get two cells right next to each other, which are both saved. That's unfortunate, but, well, they won't eat up that much disk space. We're still saving a lot by not going with a very dense saving scheme in the non-interesting parts of the simulation. Next, maybe we could actually plot one of those VDFs. So we'll just copy that line there, change it to plot VDF, and now we will select coordinates, for example, around there. That will be approximately 10.8 in X and 3.8 in Y. So 10.8, 3.8, and 0 in the Z coordinate. It's giving us some information. Oh, yes. This, my friends, is a Vlasiator VDF, if ever. So we have quite a bit of interesting particle populations going all over the place. Let's see. I'm going to set the threshold to 0. This will now show you what the actual internal structure looks like more. So we've got a bit of artifacts there, but you can see the sort of edges there. See, we don't have, sometimes sadly when the dynamic range isn't handled properly, we lose the tick marks there. That's something that's been on my to-do list for quite some time. What about letting the threshold be the regular one again, and slice thickness? I'm using tab completion here, and let's set it to just 0, which is infinite thickness, so to speak. And now, instead of doing a slice through the VDF, we integrated it and flattened it. So we've got the Vx, Vy coordinate systems. The 0 point is here. So this is now the solar wind core, which has been slowed down somewhat, but not a huge deal yet. And these are particles reflected from the bow shock and streaming back upstream. This is some of the strongest points of Vlasiator, being able to model the foreshock in such incredible detail. And this is not gathering, sampling particles over some length of time, but it's actually a snapshot of the distributions at a singular moment. But let's see, what about if we change this so that instead of having the Vx and Vy, we could do some other directions? Let's try YZ. What'll that look like? Oops. Oh boy, yeah. So here we now have, again, the solar wind core and gyrating particles. We've got full gyrations, and then you've got these crescent-shaped semi-gyrations. Now, what about we use our information about the magnetic field at that location? So we want to have the x-axis as the B parallel. Let's see, what do we have? We have B para and B para 1. Let's just say B para for now. This now takes the VDF and rotates it. So we have the velocity along the magnetic field on the x-axis and the B cross V direction on the y-axis. And you can see that suddenly now the reflected particles are on the left, because the magnetic field in the simulation was actually pointing from right to left. Now, I believe we have might have a way around that. Nope. Nope. Okay. What other option we had? B para 1. This, I believe, then it has the V and B cross V here. So now I cannot remember off the top of my head how to swap the direction here. Let's see. What if I use the question mark? That gives now a more common thing. So I will jump to a new, go here and do that. Now this gives us the signature and all the keywords. Ah, it wasn't swap coordinates, it was coordinate swap, but of course. So let's try that. Coordinate swap active. Let's go back to the previous one. And it is thinking, and oh no, this one actually swapped them that way around. We have some more information here. Okay, I think we now have a feature request from myself. I want to be able to swap the x-axis direction. Oh, well, I mean, it's correct. It is still the velocity in the direction of the magnetic field or not. But sometimes it can be a bit, it would be nicer maybe to have it in the, well, of course, then we can go back to the XY plane. And that's it. So now it's again flowing to the right. Then we also have B-perp, which looks like this. So this is a bit like the YZ slice, because the magnetic field in this simulation is mostly along the X direction. We again see like a full gyration and then the semi-gyrations. And we can, of course, jump to different locations in the simulation. Let's go a bit further out from the bow shock. And we can see that instead of these full circles outside, we've got a bit more of a generalized cap. Let's see what that looks like in the parallel direction. And yes, we now have the main reflected bulk here, but then some of these weird reaches. Okay, do we have questions at this time? So I think at this point, I could stop talking and just point you to the exercises here again. So we tried altering the color scale. We've tried editing the minimum and maximum values. You can turn the masking on or off. You can overlay the data, as I showed in the presentation slides. You give a keyword variable to the vectors. You can determine how many they are, how tightly packed, what color map to use, what sizes to use, and streamlining as well. So recommendations are to use this question mark functionality. That will give you both first a list of the keywords accepted by the function and this doc string, which really should actually give all the necessary information. If you find outdated information or confusing information or lacking functionality, please add it to the HackMD, and we will strive to fulfill all of your needs. There's even some example usage here. Okay. I will stop sharing now. If someone else wants to showcase a problem, you can share it on HackMD, or if you want to, you can also probably join the Zoom and share your screen and we can look at it. And also, if you have issues with getting the Jupyter launching on LUMI, then let us know. We'll try to help, but I think the instructions don't have too many tripping points. Just clone your analyzer repo and then use the instructions from the pages to set the directory access correctly, and it should work just like that.